latch up, we say that it can reduce short channel effect. Then another thing is that it can reduce the parasitic capacitance. So let's take a look at the middle. This is a bulk transistor. You know that we have this capacitor. This is COX. We also have a capacitor between here. Because this is a PN junction, this is CSB. We also have a capacitor here. When it is heavily depleted, it's very wide, CDB, right? So in a transistor, we actually have CSB, CDB, and also this COX, which is here. We have other thing that this is related to the depletion. This is what we usually see depletion. And then you have some fringing capacitance between the gate and also the gate and source and the gate, right? So which we ignore here. We don't talk about this. Our goal here is to discuss these two, CSB, CDB, which are this and this. When I have the insulator, then I have very small dB. Why? Because it's equals to the epsilon divided by the thickness. And this insulator is thick. If you rely on the depletion layer, they are relatively thin. But with this one, I can have a thick TOX. So as a result, when TOX increase, then the capacitance CDB reduce. Now, this is important for high frequency operation. By removing this or making this so small, very tiny, negligible, then it will be much faster. It's good for high speed applications. Is that okay? So this one not just cut off the latch up leakage. Also, what did we do just now? Improve the short channel effect, but also reduce the parasitic capacitance. A lot of advantage going to SOI.
Can we close the discussion from the last slide? I was just trying to understand on the Dibble improvement at 4 Kelvin. Yeah, so basically what you're saying is this Dibble improvement at 4 Kelvin is not due to anything device physics-wise. It's just your subthreshold slope, subthreshold swing has gone up. And that's why all these curves, they kind of bundle together. And you don't see a big difference between linear mode and saturation mode operation. Did I get it right?
Now, maybe I'm not complete. So compared to 300, yes, it is related to the improvement of the temperature because you go to lower temperature, right? You will have a better control over the barrier. But I'm trying to say the difference between them is smaller. That in a part of the reason is because it is bad at the beginning. So it's limited by the abnormal subthreshold slope.
Okay.
Yeah.
And why is you would expect the curve in that subthreshold region to sort of kind of go, in a straight line with the log scale on the y-axis, whereas one has a big bunch of kinks. So how does that fit with the subthreshold equation of the transistor?
Yeah. So this is completely because of this paper we did. We try to model it using the traps to model the subthreshold slope. And then when we do the traps, it's very difficult to make it smooth. So we do not match the experiments well. What we did is just on average, it matched the slope of the experiment, but we did not try to fix this corner. So this just because of model. These are all simulation, not experiment.
Okay.
So this is a
simulation.
This is a deficit in our modeling. So we do the step size instead of doing a continuous trap because it's a little bit difficult to set up in TCAD.
Oh, okay. These are TCAD simulations?
Yeah, this is a TCAD simulation.
Okay. Okay. Yeah. It almost kind of looks like some quantum effects. I don't know if TCAD.
Yeah, it is not. It is not. Sorry for that. So only look at this session maybe. Yeah. So so it's not a good perfect matching. But what you're saying is actually worth to study more what you said. For example, if can we make it even shorter to see more depot? You can study more, but this is just the first order explanation. Okay. Yeah. So the more you say, looks like you like a criticism in a conference that I start failing to explain perfectly. So I can be not incorrect. Okay. Yeah. So let's move forward. So let's spend some time to talk about the fabrication of SOI, right? So it will be quick. You start with a silicon wafer. There are a few methods. The first method is called SIMOX, separation by implantation of oxygen. Maybe, but I think I copied it right. I forgot, right? So SI and then MOX, okay? That's how they come up with this acronym. SIMOX, right? So what you do is this: you implant oxygen, just implant the oxygen ion with a high dose, so that they reside in this region. And then you go for a very high temperature annealing. This is very high, very close to the silicon melting point. Then they react with silicon. Then you get a thin silicon on top of silicon dioxide. The main point is that this one is still crystalline. Okay, so that is the first method. But you need high temperature annealing. Might be expensive, right? Another one is using wafer bonding. You start with a silicon wafer, and then you just do regular oxidation. For those who know semiconductor fabrication well, you know that this is easy, right? All you need to do just put the silicon in the oxide ambient, then you get silicon dioxide on top. So you can have a very high quality silicon dioxide using thermal oxidation. Then you put them together. They are bound by the van der Waals forces. I hope van der Waals, right? Okay, I hope I spell it right, right? So you just put them together. If they're clean enough, they will just bond through van der Waals forces. But then you have two very thick silicon, right? Because a silicon wafer, particularly in the past, at least 1 millimeter. So what if I want to have a 100 nanometer of silicon? What should I do? I need to polish it, right? Just like what you do in the wood shop. So you need to polish it, and then eventually it is thin enough. And you also have a high quality silicon on insulator, right? You waste the whole wafer. This is a wafer bonding, right? So it means it's going to double the initial material cost, right? The last method, which is many people using, and the company is called Soitec from France, right? They produce state-of-the-art 300 millimeter SOI wafer. So that's what they do. You start with this wafer A. Yeah, you oxidize it. This is easy, again, low cost. You implant hydrogen to it. But you're not trying to do any reaction. You just implant it with a lot of hydrogen on this layer. Then you do the wafer bonding. Again, like what we did last time. So last time we bond oxide to the silicon, right? So here again, we bond this. I flip the wafer. Look at this. This is flipped, right? So upside down. This one is bond to here. But in this book, the drawing, they flip again. But anyway, so this was the original wafer and now bond to the new wafer, right? So what do? You just apply annealing to 500 Kelvin. The hydrogen is going to expand. So you just cut it. So you implant it's just like you implant some gas into the wood, and then let the gas explode, and then you crack it. Then on top, you have a very thin layer of silicon. Remember, this part is silicon, right? Because hydrogen is the dotted line. So this is silicon, right? Just remember, this is silicon, right? So this is still silicon. Then you polish it, make it flat. And this allows you to go to a very thin oxide. And the good thing is, you can reuse this wafer, the one you just separated, for the next step to form another SOI. Instead of polishing everything away, you wasted one wafer. Here you can reuse this one. So this is called smart cut. Okay, and then with this, then you continue to build your transistor on top of it, like what you regularly do. Okay, I think I see that I have it. My cheat sheet should be when the was false. Okay. So that's all I want to say. Now you know how to fabricate it, and then on top of you just continue your regular bulk CMOS fabrication process. There are, of course, something that you need to fix it, but that is approximately what you have. Now you know what is silicon on insulator, SOI, but there are two types. One is called PD. What is called PD? Means partially depleted. Another is FD, which means fully depleted, right? So you can buy them from, what controls whether it's partial or fully depleted? So let's look at this again. This is oxide, okay? And this is the silicon, so we call it SOI, right? So you be careful when people say SOI, sometimes they mean the whole wafer, sometimes it's talking about this silicon, because this is the silicon on insulator. So they can be talking about this layer. Sorry, my internet has some problem, right? So let me say again, you have partially depleted and fully depleted. And this is the silicon. Sometimes people call it SOI, silicon on insulator, right? And if this is thick enough, right? Think about if this is pretty thick. Isn't that it will behave like a bulk transistor? So you have a depletion region, and this is just like the bulk or like the substrate. In the bulk transistor. Okay? Now, if I make it very thin, then when I turn it on, then the whole thing is depleted. Because just think about this. Depletion region is that thick, right? Then let me make the transistor, make the SOI really thin, right? Then it is fully depleted. Now, then what is the difference here? The main point is that in a depletion region, you have a strong electric field, right? Because it's depleted. If you remember what we did earlier about the depletion, you have an electric field. Remember, I will erase it so you won't get confused. But remember, when we talk about depletion, right? In this region, the potential is changing. So you actually have a large electric field. Maybe I keep it, right? This is the depletion region. But this region is the neutral region. You don't have electric field, right? So if I generate any carrier here, it will just stay there. It's not going to be pushed away or pulled away by the electric field, right? So that's the difference between the depletion and the quasi-neutral region. Any questions?
Is there any advantage of PDSOI compared to FDSOI?
Yeah, we do. We'll discuss this later. But one of the main advantages is what is related to this electric field that can drift away any carrier you will generate. And usually PDSOI, fully depleted SOI, has a better gate control, which we will discuss later also, right? But for now, just understand you have PDSOI and FDSOI. PDSOI, you can say, is a transition from bulk to FDSOI because you have a quasi-neutral region.
Okay. Was it also the result of these innovations were kind of result for progression in the fabrication technologies? Maybe they came up with PDSOI first before ultimately they were able to manufacture an FDSOI reliably?
That is one reason, because this need to be thin, right? How can you make 5 nanometer and 20 nanometer thick silicon uniformly on the wafer,
Yes.
right?
Yeah.
But on the other hand, PDSOI has its advantage. For example, I can bias the substrate, which allow me to change the threshold voltage for back body bias. For the body bias through the here instead of the back side. Another thing is, for FDSOI, your threshold voltage completely depending on the thickness of depletion, which is dependent on the thickness of your wafer. So if you have a variation in this thickness of silicon throughout your wafer, your threshold voltage will have a big variation. Here you are more benign because again it depends on the depletion, but however you have this neutral region, so even you have a thickness variation, the effect on the threshold voltage will be much less, right? So they do have advantage. Yes.
Well, it looks like PDSOI has two body connections. One's the back gate and the other one is what you're calling quasi-neutral region. So you would have to have two back gate voltages or body voltage control. Is that correct?
You can do that. Yes, you can. No, I'm wrong. You can only go through this region because if you try to connect from this back side, this is neutral. So you basically cannot control the top layer unless you try to form an inversion layer here. So usually you will go through this part. On the other hand, for FDSOI, because this is depleted, so if you have a back gate bias, you will be able to control more effectively.
Okay.
Yeah, but we will discuss this a little bit more later. Okay. So just remember we have PDSOI and FDSOI. So why? Why is so important? This is from lecture 4. I just repeat it. Remember the subthreshold swing? Subthreshold swing is saying that how much gate voltage I need to change in order to increase the current by 10 times. So we say usually it's in the order of 60 to 100 millivolt per decade. Means I need to increase by 60 millivolt at least in the gate or 100 millivolt at the gate so that the current increase by 10 times. But at that time we say that it depends on the N. What is the N? You have a oxide, then you have a capacitor, right? This is your N plus, this is your N plus. This is the region you form the channel. But at the same time, you also have a depletion region, right? This is the depletion region. It is also, this is CD, this is COX. It is also depending on this CD, right? The depletion layer, just due to potential divider effect. So N equal to 1 plus CD divided by COX. If your CD depletion region is very thick, right, then you have a very good subthreshold swing. If you have a large capacitance, that is not good. Remember this? Now, if you go to fully depleted SOI, let's look at this. A lot of capacitor, right? But so to make it simple, I would say let's remove all this SS. These are related to the traps. Okay? So let's assume there's no traps. This is for bulk. Look at this. This is for bulk. Isn't that is exactly what we discussed earlier? 1 plus CD divided by COX, which is equals to N. Right? Now, let's look at the capacitance in this fully depleted SOI. You first have this COX1, which is here. But it is fully depleted, right? So you also have this one CSI because it's fully depleted, which is here. Then what else? I also have, after that, I have this one, SIMOX2, which is due to the barium oxide, right? SOI is here. This is barium oxide. You might also have the substrate, which is not that important, but they show it here. Here you also have depletion. Here, C sub. You might have some depletion. Depends on the electrostatics. So as a result, this N becomes very complicated because it has this X here because they have the SS. Let's do not look at it. If you ignore all the SS, what you get is this. 1 plus, what is that? COX, but you have CSI parallel. Now, this is mathematically parallel. They are in series, right? But mathematically parallel. COX to parallel C sub. If you have or in other words, if you treat this as a whole capacitor, they are super thick. They're very thick. Unlike this CD. When you are thick capacitor, then it means what? This is very small, right? Because again, it is in parallel calculation or they are in series. So a capacitor in series gives you smaller capacitor. As a result, by using FDSOI, you have much better subthreshold slope. Or I still call it subthreshold. Some people don't like subthreshold slope. They call it subthreshold swing. Let's follow that. Subthreshold swing, right? Better. Is this okay? Basically, fully depleted SOI, because these are depleted, just like insulator. Then you have a big insulator, so you have a very small capacitor. Very small capacitor compared to this CD in bulk. Okay?
Question.
Yeah.
Can you comment what happened to CD in the FDSOI case? I didn't follow that.
You don't have C. Oh, yeah, sorry. I saw my internet has problem. So CD is the depletion layer in the bulk, right? But yes. The whole layer is depleted. Is this okay? Because it's fully depleted SOI, very thin. So this is insulator. And then next to it is another capacitor, which is also insulator, right? So this CD is just like CSI. Okay? But then it's in series with COX2 and also the substrate if there's any depletion at the substrate. So as a result, you have a very small capacitance for this part.
Okay, so N is smaller.
Yes.
Okay.
It means it almost equal to 1. So you almost have an ideal subthreshold slope. So at 300 Kelvin, you will get 60 millivolt per decade. I realize I have some internet instability. Let me know if you cannot hear anything so I can repeat. Okay, then let's look at the subthreshold swing. Now, if you look at this, when I change the silicon film thickness, right? You go from fully depleted to partially depleted. When you're fully depleted, do you see that it is very good at 300? This is 300 Kelvin. I did not say that, right? This is 300 Kelvin. Almost ideal subthreshold swing. 60 millivolt per decade. But once you make it thicker, you just jump to full partially depleted, right? It's just like bulk. Okay, so that is what I just explained to you. Another thing I want to emphasize is that because now you actually have top oxide, COX, also barium oxide, you can treat this as a gate also, but a very lousy gate for SOI. So you do have a front channel and also back channel. For front channel, you see that I have good subthreshold swing. This is to the left. This is to the right. For this one, it's very bad, right? Because you have very thick oxide. So let me emphasize. This is SOI. So you have N plus. This is N plus, right? Then you have a bed oxide, and then you have a front oxide, right? So what is the front channel? This one is the front channel, and you can form a channel here, right? No one say that this cannot be the channel, although it's lousy. That is the bad channel. Okay? But when you reduce temperature, it gets better. That is good. But however, you still have the abnormal subthreshold swing. Let's just look at this P-type SO, but this is FinFET. Look at this FDSOI, the triangle pointing up, right? The upside triangle. This point, it only has 1 point actually in this whole figure. But again, when you go to very low temperature, it still cannot achieve what we have. Again, that is the abnormal subthreshold slope that we discussed earlier.
Does this chart show that the FDSOI is superior in subthreshold swing compared to the bulk transistor?
Not in this chart, because now I realize that it only has one data point. So
Okay.
then now you are but if you try to compare now, you cannot just compare directly because they have different drain voltage. They from different paper, so you also don't know the gate length. So we don't compare here. Okay. Yeah.
Are we going to talk about FinFETs?
Yeah. After SOI, we talk about FinFET. But yeah, we finish SOI first. Okay. So here is very messy. I just want to give a few concepts. No need to memorize a lot of equations, right? That's why I say no need to derive. Here I want to emphasize one thing. When you reduce the temperature, the band gap will increase, as you see from here. This conduction band, right? Let me make this very clear. This is the EG band gap, and when you reduce to low temperature, the EG is larger. Okay, just the physics. Band gap will increase. At the same time, these are the Fermi level. They also will get closer to the band edge. Right? I just want you to know about this. Okay, this is Fermi level for 1E18 doping that get closer to the band edge. So what happened to the subthreshold slope when you reduce the temperature? So it's interesting. We see two slopes for FDSOI and PDSOI. But actually, I should not say that. I should say that for the same device, when you go to low temperature, right? When you reduce the temperature, then it becomes, of course, depends on the thickness. For some thickness, it becomes FDSOI. So why is that? Just what I try to say here. Because when you go to low temperature, you have a larger band gap, and you also have the Fermi level closer to the band edge. So as a result, you have a larger depletion width. Because you have a larger depletion width, think about this. If this depletion width increase, then at lower temperature, it might cover the whole silicon. Then it is just a fully depleted SOI. That is what I want to point out, right? This is the depletion width. You solve the equation, and then here you show you how the threshold voltage changes with temperature. So but this is the same when you reduce the temperature, threshold voltage for bulk will also increase, but for partial SOI, depleted SOI, it increases faster, and then eventually it becomes the FDSOI, right? So I think I see it's 47 now. I will stop here. But the only message I want you to bring back is about this slope, and it will be good to understand that the band gap increase and Fermi level is closer to the band edge at low temperature. Okay. Any questions? If no, I will stop now.
Are we gonna talk about in your fabrication